We are already done with 10 chapters from our book of Fundamentals of Heat and Mass Transfer by Incropera and Dewitt. And now we are moving towards one of the most important chapters. This chapter is like the main chapter, like the main essence of this whole course is there in this chapter. This chapter is about heat exchangers. So we are going to study the heat exchangers. This is something which is applicable. You go in the industries, okay, you see everywhere. So there are heat exchangers, okay. There is a phenomena of conduction, convection, radiation, all going through, but all going through together in heat exchangers. So that's the application-based chapter. This is where the application, this is where the real stuff is present. Okay, so this is not really that difficult chapter, but you have to understand that it's now going to combine all of the studies that you have done in the past chapters. So chapter 1 to 10 will all be there in chapter 11. So when you have a heat exchanger, so you have one fluid, you have another fluid. Obviously there is change in temperature of the two fluids and you want an exchange of heat to take place. But we don't want the fluid to mix together. So we put one fluid in one side of the heat exchanger, other fluid on the other side of the heat exchanger. And through the heat exchanger, through the solid body of the heat exchanger, the heat is transferred from the hot to the cold fluid. Okay? And this process takes place. And so you have one fluid in the inside of the inside the tubes of the heat exchanger. So that's kind of an internal flow that you have been studying in chapter number, I don't remember, I think chapter number 8. And then you have flows above it, which is the external flow. There is a possibility that on the external side, there is no, there is condensation or boiling. So you have a tube which is passing through a container, and inside the container you have liquid and there is boiling occurring. Okay, so that's chapter number 10. There is a possibility that you have free convection on either of the side, inside or outside. Okay, so there are multiple possibilities. There is possibility that you have tubes, and with the tubes you have the fins attached to them. So you have extended surfaces. Okay, so heat transfer to increase the heat transfer on one side. So then this is chapter number 3. So it's really a combination of all chapters. This chapter number 11. It's yeah, just the thermodynamics is the basics, obviously. So the thing is that this chapter is difficult, is easy in the terms that there are not much new things in it, but difficult in the sense that you need the understanding of the previous chapters to really go through it. Well, so we're going to spend a little time on this chapter this week and the next week. So 2 weeks we are going to spend only on chapter number 11. Inshallah. So this is about heat exchangers. Okay, so we're going to start with the heat exchanger types. We're going to study the overall heat transfer coefficient. Then we're going to study the heat exchanger analysis, the log mean temperature difference, the effectiveness NTU method. Okay, then we are going to study the heat exchanger design and performance calculations, and that's it. Okay. So the process of heat exchange between two fluids that are at different temperatures and separated by a solid wall. Obviously, temperature difference is important. Without temperature difference, there is no heat exchange. And they are separated by a solid wall, because the two fluids which are exchanging heat, you don't want them to mix together. You want them to remain separated. So you need a separating boundary. So that separating boundary is the solid wall. Normally we make it of metal. because we want the heat exchange to take place. So we need a solid boundary which allow conduction of heat easily. So if you make a solid boundary of concrete wall, yeah, it is a solid boundary, but it will really not allow that easily heat transfer to take place. The thermal conductivity very low. Anyways, occurs in many engineering applications. The device used to implement this exchange is termed as heat exchanger. So that device, any device which is allowing the heat exchange to take place from one fluid to other fluid is heat exchanger. Okay. The objectives of this chapter is to introduce performance parameters for assessing the efficacy of a heat exchanger, and to develop methodologies for designing a heat exchanger and predicting the performance. Anyways. So let's discuss first of all the types of heat exchanger. What are the types of heat exchanger? The one very common and very simple type of heat exchanger is known as double pipe heat exchanger. So double pipe heat exchanger means you have two pipes, and this is also known as concentric flow heat exchanger. So you have one pipe inside the other pipe. Okay, so you have, this is your one pipe and this is your another pipe, and they are concentric, means their centers are same. They have the same centers. Okay, so one fluid will move through the inner pipe and the other fluid will move through the annulus region. So you remember, this is the annulus region. This is the annulus region. This is the inner pipe. Okay, so one fluid will move through the annulus region, one fluid will move through the inner pipe. And obviously, if there is temperature difference between the two fluids, so the heat will transfer. If this is hot, this is cold, so heat will transfer from hot to cold. If this is hot, this is cold, then heat will transfer from hot to cold. Okay, but the two fluids are separated, and one is moving inside, while other is moving in the annular region. And if there is temperature difference, then there will be heat transfer. As simple as that. So this is known as concentric flow double pipe heat exchanger. Okay, so if you make it like this, so you have an inner pipe. In the inner pipe you have one flow, then in the outer pipe you have, in the annulus region, you have another fluid. Okay, and as they flow, so there will be heat exchange. Now within this double pipe concentric heat exchanger, there are two possibilities. Or you can say there are two sub-classifications. One is known as parallel flow, other is known as counter flow. So suppose your one fluid is moving in this direction and other fluid is also moving in the same direction, then this is parallel flow. If one fluid is moving in this direction but the other fluid is moving in the opposite direction, then this is counter flow, right? So it's not about the direction like this or this. If the two fluids are opposing each other in motion, then this is counter flow. This is counter flow. This is also counter flow.
It will affect the way the heat transfer.
Yes, it will affect, and we are going to study that how it will affect. Okay. So this is parallel flow heat exchanger. So you see here, one fluid is entering here, and this is the annulus region, goes into the annulus region, then comes out. The other fluid is entering from the center pipe and moving, but they both are moving in the same direction. So it's a parallel flow, double pipe, concentric, parallel flow heat exchanger. This is, the inner fluid is moving in this direction, and the outer fluid enters from the top, goes into the annular region, passes through the annular region, then goes down. So basically, in the main body of the heat exchanger, one fluid is moving in this direction, other fluid is moving in this direction. So this is basically a counterflow heat exchanger. Do you understand the concept of parallel flow? Do you understand the concept of counterflow? Do you understand why it is called double pipe heat exchanger? Because there are two pipes. You understand why it is concentric flow?
Yes.
Because the centers of the two pipes are
It
same.
has to be pipe.
Yeah, it has to be pipe. It has to be pipe. Right now, for this heat exchanger, this type of heat exchanger, it has to be pipe. That's why it's.
Study?
Hmm?
We study or what?
We?
We study here or there is another thing, square?
No, no, no. We study here.
What do you mean?
I couldn't understand actually your question.
Never mind.
Are you asking that we studied this before?
No. There is another type.
No, there are the types of heat exchangers. There are the type of heat exchangers. But this is one type and it has a specific name, double pipe heat exchanger. Okay? So this is concentric flow double pipe heat exchanger. Let's move towards the other type of heat exchanger. Okay? So one other type of heat exchanger is a cross flow. Cross flow heat exchanger. Now cross flow heat exchanger, as the name implies, the flow are neither parallel nor counter, they are cross, means perpendicular to each other. So one flow is in this direction, other flow is perpendicular to this direction. Okay? So if this is my flow is through this tube, so this is cross flow. Any flow in the perpendicular direction is a cross flow. Now in cross flow heat exchanger we have two categories. We could have finned, we could have unfinned. So suppose you have flow in the tubes, in the pipes going, and you have another flow of air in the cross direction. Okay? So there are no fins. This is just pipe. The flow is across the pipes. Okay? So this is unfinned. But we can put fins. We can put a number of plates here. If you put a number of plates, these plates are connected with the pipes, are attached with the pipes. So there will be conduction from the pipe to the plate. And then these plates will behave as fin. This is an added heat exchange area. Okay? So this is fin, but this is also cross flow. Flow through the pipe is like this. Air is moving in this direction. This is finned. Okay? Now within finned and unfinned, there is another categorization, mixed and unmixed flows. If you see here, one flow is through the pipes, okay, and these pipes are separated. So the flow in the pipes do not mix with each other. So the flow through the pipe is unmixed, but the flow of air, it is mixed, because the air can mix with each other while moving in the cross flow direction, right? So this is one flow one flow unmixed, this side flow mixed. On this side, if you see here, flow through the pipe, do you think it is mixed or unmixed?
Unmixed.
Unmixed. What about the flow through these tubes, these fins? This is also unmixed, because now you put the plate parallel, so any fluid which will enter in one of the gap will not mix with the other fluid until and unless it comes out of the heat exchanger. Okay? So this is with both fluids unmixed. This is with one fluid mixed and the other unmixed. This is another classification. This is actually a very important classification for the case of cross flow heat exchangers. Is it clear? So we discussed concentric flow, double pipe heat exchanger, parallel flow, counter flow, and this is the cross flow heat exchanger. Could be fin, could be unfinned. Okay, in this chapter you have a lot of stuff which I can bring from the short questions. There are a lot of stuff. I can bring you a heat exchanger in front of you, can ask you, is it unmixed? Is the flow unmixed? Is the flow mixed? Is it a cross flow? Is it a parallel flow? Is it a counter flow? So all this information which you are getting right now, consider this as important, could be brought in the short questions. This is all about the understanding. Okay? Now the most important type of heat exchanger, shell and tube heat exchangers. You heard the name of shell and tube heat exchangers before?
No.
You said, only one guy said yes.
That is.
Okay, good. So shell and tube heat exchanger is is a kind of heat exchanger as you consider you have a shell, and inside shell you have tube. But it's not just one tube. There are many tubes inside this shell. Shell is one, but inside the shell you have many tubes, right? If there is one tube, then it becomes a double pipe heat exchanger. If you have a shell and inside the shell there is only one tube, then it becomes a double pipe heat exchanger, right? But if you have many tubes, so you have one big shell, and inside one big shell, instead of having one tube, you have so many tubes. Okay? So then this is a shell and tube heat exchanger. Okay? And if you see here, so you will have one fluid which is going through the tubes, and you will have another fluid. Now we don't call it annulus region. This is not annulus region. This is just the shell side. Okay. So one fluid will be in the shell side, other fluid will be in the tubes. And if this is the kind of a heat exchanger, then it is known as shell and tube heat exchanger. It is one of the most common type of heat exchangers you will find in industries.
We will study the using of these things.
Yes. Using means what?
What we are using.
Application. All of the heat exchangers, look, application is too varied. You can apply it anywhere. Anywhere if you want a heat exchange to occur.
The one is in the fridge, behind the fridge. What about the shell?
Shell and tube heat exchangers. Shell and tube heat exchangers, if you have, for example, you need to supply some process heat in the industry. Okay, so suppose you have two fluids and both are none of them is gas, both are liquids. So for the liquids, shell and tube heat exchanger works perfectly fine. If you have gases, then because gas has low coefficient of heat transfer, so you need to extend the area. That's why you need fins. So we use fin, cross flow, these type of heat exchangers. So if you see the back of the condenser tubes, so you find fins there. The reason is that air has low coefficient of heat transfer. If you cannot increase the coefficient of heat transfer, the only way to increase heat transfer is by increasing the area. So you put fins there. Okay. For the case of the liquids, most of the time we use shell and tube heat exchanger. Shell and tube heat exchanger is a very compact device and it's very effective. Okay. So let's study the construction. So in the shell and tube heat exchanger, what we want is that we have fluid in the tubes, going through the tubes, and then we have the fluid which is there in the shell region. Okay, but we want it to flow as a cross flow. We want the fluid in the shell to move in the cross flow direction with the tubes. Now this is a trouble because you enter the fluid from one side and it will move either parallel or counter. How can we make it to move cross flow? So in order to make the fluid move cross flow, what we do is that we put baffles. Okay, so this is your shell. Inside the shell you have many tubes. Okay, inside the shell you have many tubes, and so you have the fluid entering into the shell. So what you do is that if I put a plate here, so the fluid cannot move directly from here to there. In order to move from here to there, it has to pass through this direction until it reaches here. Then if I put a plate another here, so now the fluid cannot move like this. It will have to move up, and then so the fluid moves it like this. So you understand? All the time, the fluid moves in the cross direction to the, sine waves. Okay? So it's like a zigzag path. Zigzag path. So at any instant, the motion of the fluid in the shell is cross with respect to the motion of the fluid in the tubes. Now you can see here, that's why I brought this shell and tube heat exchanger. This is a model, small model of shell and tube heat exchanger. So that if you see here, this tube here is made up of glass, so you can see inside. Okay, so there are so many tubes inside. So many tubes inside, okay? And if you see here, there are plates. These plates are known as baffles. Baffles. They're like kind of restriction, okay? So the fluid which enters from here, cannot move from here to there until it passes through the bottom of the baffle, then enter in this direction. Then now the bottom baffle is almost up to 75% of this area. So it has to move up and then pass through the opening, then enter cross flow, then pass through the opening, and like this. Okay? So these are the baffles here. So through these baffles, you can see the tubes are also passing through these baffles, but the shell side fluid cannot pass from one direction. It has to pass through the opening. Okay? Have a look at it. Have a look at it one by one. We can put any kind of fluid. We can put water over it. Okay? So you can see you have tubes, many tubes inside the shell, and then you have baffles.
We will have experiment on this.
We
will have experiment.
No, you don't have experiment on this, but because experiment would be what? It will be just one fluid pass. In the experiment, you have to push the button to start the experiment. You have to wait for it to stabilize, then you have to take the reading. It's important what you see inside. And you can measure temperature. Yes. Why is rust? We'll come to it. Fouling. Good. You remember fouling? I asked you to study about fouling in chapter number 1, I think.
What?
Fouling.
Fouling process.
So this is a shell and tube. This is a model of a shell and tube heat exchanger. So how does it happen? So you have a tube. You have many tubes inside. Okay, and this is, you can say, the header region. Okay, so your fluid which has to pass through the tube enter from here, and then goes into the header region. Now header region is like just an opening, and through this many tubes are opened. So then the fluid from the header region enters into the tubes. Fluid from the header region enters into the tubes, passes through all the tubes, then mix again here in the header region and come out. So this is, throughout the body of the heat exchanger, fluid remain unmixed. Okay? So we have this is how the fluid moves within the tubes. Within the shell side, on the shell side, fluid enters from the top, then enters into the shell, then passes in the cross flow direction throughout, enter into the shell, okay, and then come out from here. Okay, so it's kind of a cross flow heat exchange. It's kind of a cross flow heat exchange, but this is not just simple cross flow. Because if you see here, let's say the fluid is entering from here and leaving from here. So this is the direction of fluid motion. If I am making the other fluid, shell side fluid, to enter from here and leave from here, although the shell side fluid is in cross flow direction, but it is also counter flow direction.
Yes.
See, if it is entering from here and leaving from here, so on a bird's view picture, on an overall picture, the shell side fluid is moving like this. The tube side fluid is moving like this. So it is cross flow as well as counter flow. That's why we give it a name as cross counter flow. Got it? Suppose if the fluid is moving from here, tube side, and moving in this direction, and I put the shell side fluid from here, and then it moves through the baffles until it comes out from here. So this is what kind of? This is called cross parallel flow.
It is discount.
Sorry?
But the thing we are selling is discount.
Yeah, but we can make a cross parallel flow as well. Okay, so we can have cross counter flow, we can have cross parallel flow in the shell and tube heat exchanger. So now look at the picture. You have a shell, you have so many tubes. In the model that I have shown you, the tube side flow enters from here and leaves from here, but here it is shown like tube side flow enters from here and leaves from here. But anyways, this is the header area. This is the header area. Header area is the one through which it is connecting to many tubes. So the fluid enters, so here in this case fluid enters like this, and then again recollect at the header area and goes out. And in the shell side, fluid enters from here at the top. Here it is shown here that the fluid leaves from the bottom, but in our case it enters from the top, leaves from the top, but on the other side. Okay, so it moves, it enters from here, then because of the baffle cannot move directly, so it moves in the cross flow direction, but this is a cross counter flow direction until it escapes. And these are the baffles. So you have a shell, you have tubes, you have header, you have baffles, and that's make up a shell and tube heat exchanger. So you need to have an inlet for the shell side fluid, you need to have an outlet for the shell side fluid, you need to have an inlet for the tube side fluid, you need to have an outlet for the tube side fluid. Okay, it depends, it will always be cross, but it depends if it is parallel flow or counter flow. Okay. Now this is shell and tube heat exchanger with one shell pass and one tube pass. Now it is important for you to understand the passes. This is one shell pass and one tube pass. So the tube side fluid enters and then pass through the length of the heat exchanger one time and leaves out. Right? Shell side fluid enters, pass through the body of the heat exchanger one time and leaves out. That's why shell side one pass, tube side one pass.
Go away?
Hmm?
Where does go? Where?
Exit wherever you want to take it out. It leaves the heat exchanger. It enters the heat exchanger body, passes through the body of the heat exchanger one time, and then leaves the heat exchanger body, and then it is used wherever you want to use it. Okay? Is it clear? So this is one shell pass, one tube pass. Shell and tube heat exchanger. Now there is possibility that you can have more than one passes. So let's see this. This is shell and tube heat exchanger, one shell pass, two tube passes. So a number of tubes, maybe let's say 10 tubes are entering here. 10 tubes are entering here. They pass through the shell body, then make a U-turn, then pass again through the shell body and exits here. So in this case, your inlet header is here, your outlet header is here. Both headers are at the same place.
go on back.
Okay, but they are separated, but at the same position. Okay, at the same side. So let's say 10 tubes enter from here, pass through the heat exchange body, pass through the shell body, make a U-turn, then again pass through the shell body and leaves from here. So now you have shell and tube heat exchanger. This is what would be the kind of this shell and tube heat exchanger? You have baffles. So shell side, it is one pass. Shell side fluid enters from here and then pass through the body and leaves here. That's it. One pass. Shell side body, one pass. But tube side body, there are two passes. First, it enters and pass through the body, then take a U-turn, then move through the body again. Okay? So tube side, two pass, shell side, one pass. Okay? So for the tube side, if you see here, because of the baffles, it's always cross flow. But on the first half of the tube pass, for the first pass, it is parallel. For the second pass, it is counter. So now we don't say parallel or counter, because both are occurring at the same time. Okay? It's just shell and tube heat exchanger, one shell pass, two tube passes. If it is one pass shell, one pass tube, then you have to tell whether it is counter or parallel. Okay? Otherwise, you don't need to tell. There will be, both will be there in any case. So this is shell and tube heat exchanger, one shell pass, two tube passes. The next example is a shell and tube heat exchanger with two shell pass and four tube passes. Look at it.
Oh my God.
This is a shell and tube heat exchanger with two shell passes and four tube passes. So look at see the shell side fluid. Shell side fluid enters into the shell and tube heat exchanger, passes in the cross flow because of the baffles, passes in the cross flow direction. Then after that enters into another shell.
We have two more than one.
So it's like two shells, but they are not actually, it's in the diagram it shows as two separate shells. In reality, this is one shell, just separated by a plate in between.
Yes.
Okay? So you have one shell pass. So you have two shell passes. So suppose you have this shell and tube heat exchanger, this one shell, but if I plate in between, okay, so the fluid will enter, pass through one shell, and then return back, pass through the shell again, and goes down. Just plate in between, separating plate. So now it is two shell passes. Why two shell passes? Because the fluid, shell side fluid, passes through the heat exchanger body two times. One time in one direction and then one time in the other direction. Is clear? So this is two shell pass and there are four tube passes. If you see here, the tube inlet here, so let's say 10 tubes are entering or 20 tubes are entering. Okay, and all of these tubes passes through the shell body and then take a U-turn, then pass through the shell body again, then take a U-turn, pass through the shell body again, then take another U-turn, pass through the shell body again, and then leaves. So you have an inlet header here, you have outlet header here. It's clear? So you can have 3 shell passes and 6 tube passes. Infinity and infinity multiplied by 2 tube passes. Do you understand this? Okay. So this is shell and tube heat exchanger. Could be some single pass, could be multiple passes. On the shell side as well, on the tube side as well. Okay. We have the baffles which make the flow, which keep the flow cross flow all the time. So anytime if you consider any point, any section, every time you will find that the flow is in a cross flow direction with the tubes. This is because of the baffles. Okay. So baffles are used to establish a cross flow and to induce turbulent mixing of the shell side fluid, both of which enhance convection. So because of baffles, two things happen. One thing is that the flow becomes cross, and the second thing is that there is a lot of mixing, turbulence, and turbulence also increases the heat transfer. Okay. Our objective is to enhance heat transfer. So do you understand the construction and the design of shell and tube heat exchanger or not? Is there anything in it that you do not understand? You can ask. This is very important. Consider this slide as very important because this is a heaven slide for me. I can bring tons of questions from here. There's so many things. Okay.
Well, you didn't.
Huh?
You didn't.
Okay. Okay, so we have studied double pipe heat exchanger, concentric flow, parallel flow, counter flow. We studied cross flow heat exchangers, finned, unfinned, mixed, unmixed flows. Then we studied shell and tube heat exchanger, cross counter flow, and we studied one pass shell side, two pass tube side, and two pass shell side, and things like that. So now let's move towards another type of heat exchangers which are normally known as compact heat exchangers. Now compact heat exchangers are, we can have multiple types of compact heat. First of all, these are compact heat exchangers. So that means the whole heat exchanger surface is compacted. Okay. So in a small area, in a small volume, you have a lot of heat transfer area. In a small volume, you have a lot of heat transfer area. You know, the world's most compact heat exchanger is what? The world's most compact heat exchanger is our lungs. Our lungs are the most efficient and world's most compact heat exchanger. Within the small volume of our lung, the heat transfer surface area is maximum. You cannot have more than that heat transfer surface area within that volume. Okay. Anyways, so there are multiple types of compact heat exchanger. We can have a fin tube compact heat exchanger with flat tubes and continuous plate fins. So these are the flat tubes. Flat tubes means rectangular shaped tubes. Rectangular shaped tubes, and these are the fin plates. It's similar to the cross flow type that you saw before, cross flow heat exchanger. Okay. Then you can have fin tube as circular tubes and continuous plate fins. So this is exactly the same as you saw before in the cross flow. Okay. So you have tubes, and these tubes are all connected through these plate fins. So there will be cross flow, and so this is a compact heat exchanger. Okay. Then you can have fin tubes, circular tubes, and circular fins. Fins are also circular and tubes are also circular, like this. So multiple tubes, but for each tube you have fins, circular fins around. You also solved one problem related to this in chapter number 3.
Yes, we did.
In chapter 3, when we were studying the fins, so we studied one problem related to this example, where you have a cylinder and you have circular fins, 5 circular fins around it.
Yes,
No, I think it was 6.
it was difficult.
It was 6.
No, 5. So this is circular tube, circular fins. Then you can have plate fin heat exchanger. Could have single pass. Single pass means, okay, so plate fin heat exchanger is again one of the most common type of heat exchangers. It's here, we'll show you. Okay, so in the plate fin heat exchanger, the idea is that you put a number of plates, 1, 2, 3, 4, 5, 6, okay, and you make the fluid, one fluid to pass through alternate plates like this, other fluid to pass through the other set of plates in the cross flow direction. Or you can make counter flow as well. Let's say if it is a counter flow, then the fluid will other fluid will pass through like this, right? So you have many plates, and between alternating plates, you have one type of fluid, and the others of the other alternating plates, you have the other type of fluids. Is it clear? So instead of putting now in tubes, we are putting it in plates. So multiple plates layers. So between, so if I have, let's say, 4 plate layers, okay, or let's say 7 plate layers, okay. So I will make one fluid to pass through this region, the same fluid pass through this region, same fluid pass through this region, and the other fluid to pass through the other region. So if there is temperature difference between the two fluids, then the heat transfer will occur. These plates are the separating boundary. Okay. On the board, I can only show you in the counterflow direction, but in many cases we make it cross flow. Okay. So these are the plates. So one fluid moving in this direction, other fluid moving in this direction through the alternating plates. If it is a single pass, so the fluid will enter through will enter into the heat exchanger body one time and will leave the heat exchanger body after passing through it. If it is more than one pass, so it will take a U-turn and then move through the body again, then take a U-turn, move through the body again, like that. So this is one pass. So one fluid enters in this direction, other fluid enters in this direction. And as they pass through the heat exchanger body, that's it, they leave. If there are more than one pass, then you see here, then they take U-turn. Then the fluid takes U-turn. Similarly, this fluid enters from here to there. Now, in the plate fin or plate fin heat exchanger, this is an example of plate fin heat exchanger. Okay, it's as simple as that. You can see here many plates here. Okay, they're
Very small.
very small. Spacing is very small.
Flowing.
You see, even if you have a crack, the fluid will flow through the crack. It's an opening. You need an opening. That's it. If there is an opening, fluid will flow through the opening. So we don't need to provide a lot of opening. We can provide very small opening, and the fluid will pass through it very quickly. But the good thing about is that it is very compact. All plates joined together, very small opening. The whole heat exchanger, you can take it in your hand. It's very compact. This is the major. For most of the time, you have limitation of the space. You cannot specify a room for a heat exchanger. That this room is there for just one heat exchanger. No. For example, in the car, you need to put a heat exchanger in your car, so you don't have infinite space. You have limitations in space. Okay, so you need a compact heat exchanger there. So it depends where you are using it. Okay, what is the application? Many things. But the thing is that this, if you see here, this is the construction of the plate fin heat exchanger. Plate fin, because all these plates acts as fins. Okay, so you have so many plates. They are all braced together. Okay, so one fluid enters from here. Now how does it work is that a fluid enters from one direction. So the fluid enters from one direction, okay, and then you have an opening here, then you have an opening here, then you have an opening here, okay, and this area is closed. Okay, and similarly another fluid enters from here, and you have an opening here, you have an opening here, you have an opening here. Okay, so alternate plate have alternate openings, so that one fluid can. So this entrance tube acts as an entrance header. From here it is distributed to different plates, pass through the plate, then all collected back here comes out. For the other fluid, it enters from another header and distribute to different plates, pass through these plates, return back from here. So we can also have a cross flow arrangement here, we can have a counter flow arrangement here, we can have a parallel flow arrangement here. All three arrangements are possible. If one fluid is internally moving in this direction, other fluid is moving in this direction, this is a counter flow arrangement. If both the fluids are moving in this direction, then parallel flow. If we make such that one fluid is moving in this direction, other fluid is moving in the cross direction, then it's a cross flow. Okay, so we can have parallel flow arrangement in it, we can have a counter flow arrangement in it, we can have a cross flow arrangement in it. Most of the time the cross flow arrangement is the most preferable. Okay, so now what we do is that in the industry, now you have two plates. This is one plate, this is another plate, and a fluid will pass through these plates. Okay, so what industries do is that they put certain feature. So let's say if I see the plate here, okay, this is my plate, this is one of the plate, okay, and I know the fluid will pass through the plate. So now if we make certain feature here, this feature will behave as kind of a fin. If you see here, they also made a feature here. This is plate, and do you see here on the plate, these features behave as fins.
Small fins.
So they act for two things. First of all, the flow will not be smooth, there will be turbulence. Turbulence is good, because when you have turbulence, you have large heat exchange. Okay, and secondly, they will add certain more heat transfer area. They will add a little more heat transfer area, but the amount of addition of heat transfer area is very minimum. The larger objective is the turbulence. You don't want the flow to be smooth as it passes through the plate. You want the flow to be a lot turbulent. So how to produce turbulence? So here, right now, they have put here just small strips on the plate, and these strips are present on each plate, on each side. Okay, but in reality, this is just to show here. In industry, they don't put strip, they put a pattern, and that pattern is known as chevron pattern. Chevron is also the name of a company. It's based on that they put the pattern. So chevron pattern is like this. Okay, chevron. Okay, so chevron pattern is like this. Okay, so it's something like embossed, wavy. So the fluid when passed through this pattern, so there will be a lot of turbulence in it. Okay, and it's like this. So here it was because this is a very small model made, so they did not put the chevron type embossing. It was just plate.
What are these black plates?
These are all plates,
Yes.
one over the other.
Okay, and the upper one?
The upper one,
The glass.
the glass, we just put the glass so that you can see. Otherwise, there is no glass.
Also
It-
the metal as well. This metal as well.
Everything metal.
I mean at the bottom.
Yes. The glass we just put so that you can see inside.
Okay, and also this one?
This one also. Yes.
You don't need that.
No.
We need it.
No.
No, we don't.
So this is a model of a plate heat exchanger. In industries, you have as big plate heat exchangers as the size of this room. In industries, You have as big plate heat exchangers as the size of this room. Very big ones. Obviously, we have lots of energy we need to transfer. Sorry, you asked something?
No. I got it.
So do you have an understanding of the plate heat exchanger? How does it look like? Okay, how does it function, work? Just you have alternating plates and you make the fluid to pass through it. So you studied the plate heat exchangers. These are known as plate heat exchangers. Sometimes plate fin, sometimes plate heat exchangers. Okay, then we have the cross flow heat exchangers, we have shell and tube heat exchangers, we have concentric pipe, parallel flow, counterflow heat exchangers. So we have discussed almost the most common and the major type of heat exchangers. We have discussed them, and I have also shown you the most. We also have in our lab the concentric tube heat exchanger, but it was useless to bring it because it was not made up of glass material, so you cannot see inside. What you just see is one tube. so I thought it's useless to bring it. Okay, so now let's move towards the other topic, the overall heat transfer coefficient. Now, in order to find that this overall heat transfer coefficient, now it's like you move back to chapter number 3. For this chapter number 3 is very important, whether you like it or not. Okay, so we are discussing a lot about fins.
Yes.
We are discussing a lot about fins. So fins you studied in chapter number 3. So I think it's time that you see some videos again. Okay, and now suppose you have a heat exchange. So basically in heat exchangers, what's happening? You have one fluid on one side, the other fluid on the other side, and you have a separating wall. Okay, so suppose this is your wall. We are not discussing that this might be a tube, small section of the tube. Okay, so this is your wall. On one side you have hot fluid, on the other side you have cold fluid. I have put it in the counter direction, my choice. Okay, so on one side I have the hot fluid, on the other side I have the cold fluid. So obviously what will happen? Heat will transfer.
From hot to cold.
From hot to cold. Okay, this is my wall, separating wall. So heat will transfer in this direction, from hot to the cold. Okay, now if I want to see that what are the resistances?
Convection and conduction.
So first of all, there is possibility that I can have fins here. Suppose I have fins here, and suppose I also have fins here. Okay, suppose I also have fins here. So, and now one important point here comes is, whenever you have flow, so most of the time the fluid is not clean. Clean means there are some impurities in the fluid. So suppose if you are making benzene to flow, so a not clean benzene means there is some impurities along with benzene in it. Not clean water, you understand.
Unimpure.
So you have salt, you have something in it, some dirt, which always comes with the flow. That's the life, that's the world. Okay, So there will always be impurities, and what will these impurities do? They continuously come in contact with the wall, and then some scales, something develop, a new surface, a new layer is developed at this surface, and this new layer is of the dirt, impurities. Sometimes if you are making the salty water, the water from the sea, if you are making this to pass through it, so there will be a layer of salt deposited here. Now any deposit which comes here is known as fouling, because this makes an additional layer, an additional resistance for the heat transfer. If heat wants to transfer from here to here, it has to pass through now this additional layer. Okay, and this is not a conductive layer. I mean, it's not something which it's going to prove as a resistance to the heat transfer. Okay, its conductivity is less. So this layer which develops, and now this layer could develop on both sides. We have a hot fluid on one side, we have a cold fluid on one side, and both fluid could be impure. Both fluids could have impurities in it, and these impurities then develop and on the surface of the wall where the heat transfer occurs and act as fouling. So we have fouling on the hot side, we have fouling on the cold side. Both sides we have fouling. Normally when the engineers design heat exchangers, they keep that in mind, that what would be the fouling, what will be the factor of fouling. You don't design heat exchanger for 1 or 2 weeks. You design heat exchanger to work for a long period of time, 10 years. So you keep that in mind, that in 10 years, how much fouling will be developed. It will be a factor of time, it will develop with time. But you have to keep that in mind, that after 10 years, how much will be the fouling. So you already keep that in your consideration while designing the heat exchanger, that this resistance will be there, even if it is not there in the beginning. Okay. So fouling, this is one of the reasons. There is another reason for fouling. Sometimes the fluid reacts with the wall. Now suppose if your wall is made up of metal, iron, and the fluid is water, so there is a possibility of corrosion. Okay, and the corrosion itself develops as a layer on the surface. So if you see here, these are corroded tubes. You see here the layer of corrosion at the top. You see here the dirt.
Dirty tube.
So this is like the example of fouling. The fouling occurs like this. See the tubes inside. See the dirt on it. Okay. These dirt acts as a separate layer. Okay. So this is an example. We have purposefully made it like this to show you the fouling. we have a clean one in lab as well. Huh?
I don't think so.
We have a clean one in lab.
Purposely dust.
Okay. So we have so you see the fouling. The fouling could be because of 2 reasons. Okay, could be because of the impurities which come, or could be because of the reaction of the fluid with the wall. Okay, and it does a lot of damage. You see these examples here. Sometimes it totally stops the flow. Okay, sometimes it develops. You see this whole big layer. These are the fouling.
This layer is just fouling?
This thickness is just fouling. Okay, so you see here all these tubes, all the surface, total fouling. So this fouling is a major concern, obviously, and for the designers of heat exchangers, they must take into consideration that what kind of flow is going through it and how much is the fouling expected. And once you design the heat exchangers, then it's not possible to really do the cleaning inside. Okay, yeah, there are certain ways we can try, but obviously it's not really that much viable. Anyways, so now we come back here. So we have the wall, and on the two sides of the walls we can have fins, and on the one side of the wall we have the hot fluid, on the other side of the wall we have the cold fluid, and there is possibility that you have fouling on both sides. Okay. So if I want to know that what is the heat transfer circuit, so the heat transfer circuit will be, first of all, if I start from, let's say, from this side, so TC. From TC, first of all, you will have convection resistance. Okay. Then after convection resistance, you will have
Contact resistance.
the fouling resistance.
Then contact.
No, contact resistance. We assume that these fins are embedded inside. Okay, so there is no contact resistance here. Okay. So then this is the cold side fouling. Okay. After it passes through the fouling, then you will have the wall resistance, conductive resistance for the wall. Then after the wall, we have again fouling on the hot side fouling. Then after hot side fouling, we have the hot side convection. Okay, so hot side fouling, and this is convection, this is convection, this is conduction. You understand this?
Yes.
So we have from T cold to T hot, or from T hot to T cold. This is our resistance circuit.
Okay.
Okay, so you have convection, fouling, conduction, fouling, then again convection on the hot side. So if we have this thing, then we can write the overall heat transfer or overall resistance like this. Now you have to recall chapter number 3 back again.
Yes.
1 upon UA is equals to 1 upon, so it's written in different order, but let's write it here. What will be the resistance for this convection here? Resistance for the convection will be 1 upon HA, right? Okay, but you have fins.
Yes.
So efficiency of the fin you have to include in it. Okay, so that's 1 upon HA on the cold side. Is clear? Then what will be the resistance of the fouling?
This is new. This is new.
No, resistance of the fouling we also discussed there. We also have a table for the resistance of the fouling in chapter number 3. Okay. So resistance of the fouling is given. Also we have a table for the resistance of fouling here, which will be added in your book of formulas. These are the resistances of the fouling. If it is fuel oil, if it is refrigerating fluid, if it is seawater, above 50 degree, below 50 degree, then these are the fouling resistances. Okay. So if you know the fouling resistance of the cold side, whatever the cold side fluid is, based on that you will determine. Okay. Then it will be R F double dash upon N naught A. R F double dash is what? This is the fouling resistance on the cold side. Okay, but the fouling resistance on the cold side will not just be on the wall, it will be over the fins as well.
We
Right?
have to add the coefficient.
So that's why the fin efficiency you have to include it in here as well. Okay, so that's the cold side fouling resistance. Then you have the resistance of the wall. Okay, what is the resistance of the wall if it is a plain wall? What's the formula? L over Ka. But if it is a tube, suppose this is a tube, so what will be the resistance of the wall of the tube? Ln R2 upon R1 divided by 2 pi Lk.
2 by KL upon length.
No, you're saying opposite. Anyways, So this is the resistance of the wall. Depends what wall you have. Is it a plain wall? Is it a tube or whatever? Most of the time you will have tubes. Or in the plate fin heat exchanger you will have the wall. In the shell and tube you will have tubes. In the plate fin you will have the wall. Okay. Then you will have the fouling resistance again for the hot side. So if you know what is the hot side fluid, you will know what will be the fouling resistance for the hot side. Okay, so it's R F H double dash upon efficiency, overall efficiency multiplied by the overall area. Okay. Then you will have the convective resistance. So it's 1 upon N naught HA. This is for the hot side. So this makes up the complete overall heat transfer coefficient. I have told you once again, this chapter is considered as the most difficult chapter in the sense because it requires the knowledge of all the previous chapters.
Chapter number 3 only.
Chapter number 3 as well as chapter number 6, 7, 8, 9, 10. When you want to find H's, these H's will not be given.
No. Convection.
When about these H's will not be given. You have to calculate those H's from chapter number 6, 7, 8, 9, 10. Is it clear? Do you understand this formulation or not?
Yes.
This is the overall resistance. Okay.
Overall resistance or
Overall?
resistance?
Overall resistance, 1 upon HA, 1 upon UA. Basically, overall heat transfer is what? Q is equals to UA delta T, right?
And the resistance is
If resistance is this 1 upon UA is your resistance, right? So this is 1 upon UA.
We will delete one exam.
Now there is one point here important. That 1 upon UA, what about this A? This A, is it for the hot side A or the cold side A? If it is a plain wall, then it does not matter. Hot side A will be almost the same as cold side A if both have the same fins and things like that. But if it is, let's say, a pipe, so the hot side A will be different and the cold side A will be different. A is what? Pi dl, right? So D will be different for the inside or for the outside. Okay. So, but the product of UA would remain same. Okay. So UA is equals to UCAC, which is equals to UHAH. Okay. So if your AC and AH are different, on the hot side area and the cold side area are different, okay, but the product would remain same. So it does not matter whether you are taking the hot side or cold side, the product would remain same. Okay. So 1 upon UA would remain same whether you take it for the hot side or the cold side. Yeah, areas might be different, but because of the difference in area, U will also be different, such that their product would remain same. Okay. There's an example of falling.
RW is the resistance of the wall.
Resistance of the wall. Resistance of the wall only, without the fins. Okay. Our conduction, for the case of conduction, it is L upon Ka. This is our wall, right? And for the case of if the wall is a pipe, then it is ln R2 by R1 over 2 pi Lk. This is all something that you studied before.
Yes.
Chapter number 3. N naught, overall efficiency. It has formula 1 minus AF upon A multiplied by 1 minus fin efficiency. For fin efficiencies, you remember you had some charts
Yes.
that you go into the chart and find out the fin efficiency.
Yes.
If you do not remember it, then you have to probably revise it again. At least if you have the videos, go through the videos. Just one day go through the before coming for the next lecture. You should have gone through the videos. Okay.
Which video exactly?
Chapter number 3.
6 hours, 7 hours.
What's 80?
Total area. Total area. Total area means prime area plus the fin area. You remember the prime area? The unfinned area.
The area of the wall without the fence.
Area of the wall without the fence.
Chapter 3.
Chapter 3. This whole chapter 3. Okay. So, anyways. Now, efficiency of the fin. You remember if we have adiabatic fin, adiabatic tip condition, then tan hyperbolic ml over.
And we have to substitute 0.99.
Yeah. And m is equals to 2h upon kt. Do you remember what was this t?
Thickness.
Time,
There was
thickness.
a formula in the chart. There was a formula for T in the chart.
Go through it, then you will remember. Okay.
Time constant.
Allah, يا مبدع.
Down.
Okay.
كل شيء تقول.
والله العظيم down. Time constant down. Return. Time constant down.
This was chapter number 5.
I say, but not T. Not this T. Down.
Tau is time constant, yes.
Okay. But, okay.
This T for T over how?
Okay,